This time, I'd like to introduce to the audience the performance aspects of Kunlun DBMS by comparing performance of Kunlun storage, PostgreSQL, and the community MySQL 8.0. And finally, I will show the performance of Kunlun DBMS. A brief introduction about myself and our company. I founded zettadb with a top-notch team of former database kernel developers from Tencent, Huawei, and Alibaba, and we've been working on Kunlun projects for over a year, and now our team is growing quickly. We want to build Kunlun DBMS as a NewSQL distributed OLTP DBMS with industry-level robustness. It has premium scalability, availability, fault tolerance, and crash safety, and top performance. We have finished all DDL and DML functionality development, and the Kunlun DBMS is ready for POC and evaluations, and all modules are open source. And you can visit our website for more information, documentation, resources, and downloadable binary programs and Docker images, and more. This is our agenda. We will first look at the comparison of database kernel mechanisms, that is the MySQL and Postgres, and the performance implications of such differences. We will cover these aspects: the storage structures, the undo logging, the concurrency control, and the other aspects of architecture. I will assume the audience has basic knowledge of computer science and how DBMS works, and I'm not gonna go into details. We won't have enough time for that. First, let's look at storage structures or access methods of MySQL and Postgres. For MySQL, I will only cover InnoDB. In InnoDB, rows of a table are stored as a B+ tree. Its secondary indexes are also stored in B+ tree, respectively. The table uses primary key as the B+ tree's key, and if primary key is not set, InnoDB generates row ID for each row, and such a B+ tree is clustered. When a row is updated, only its latest version is stored in table file pages, and a pointer in the row header points to a chain of undo log entries stored in undo log space. If a row is deleted, InnoDB sets the deleted mark at row header, and the purge thread will later reclaim the row's space on the page. The secondary index key entry has this key structure. It contains a header and the secondary key fields and the remaining primary key fields. And InnoDB will maintain secondary key order at each row insert or key update. And InnoDB will do change buffering to improve the performance. And InnoDB will apply such buffered changes when the target page is loaded into buffer pool. If a row is updated, InnoDB will insert a new key entry only if the key fields change. If a row is deleted, InnoDB will mark the key entry deleted. That is to set a deleted mark at the key entry header, and the purge thread will later asynchronously reclaim the space of the key entry. All such changes can be buffered if change buffering is enabled. Next, let's look at the storage structures of PostgreSQL. PostgreSQL uses heap and MB tree to store the data and the data of a table and its indexes separately. The primary table is a heap. A heap stores its tuples unordered, or these tuples are in insert order. This makes the fast bulk load very quick because PostgreSQL doesn't have to arrange any order. They just can be appended into the heap file. To do a row update, Postgres leaves the old table as is in the table files page, and it will insert a full new tuple with updated fields, and it will chain up the previous version with the latest version, and it will insert index and key entries for all the indexes for this new version of the same row. To do a delete, PostgreSQL will mark the tuple deleted, and it will then leave the secondary key in the index entries as is. A primary or secondary index is an MB tree stored in a separate file, one file for one MB tree. A key entry has this format. It contains key fields and a tuple ID. The tuple ID is a physical position into the heap so that Postgres can use this TID to directly find the tuple from the heap. This means the primary key range locality is low, and TID reference means position dependence. That is, each row is pinned inside a page. It can move across a page. And it also means Postgres needs one index entry for every tuple. If a row has 10 versions, there will be 10 tuples in the heap, and there will be 10 index entries for each of the version of the same row. This causes serious index bloat. Next, let's look at undo logging. InnoDB has dedicated undo log table space. Each transaction has one insert undo segment if it does inserts, and one update undo segment if it does updates or deletes. An insert undo segment contains primary key of the newly inserted rows plus the table ID. With this information, InnoDB can find out which rows were inserted in order to delete them if it has to roll back the transaction. The update undo segment contains extra information, that is the old values of the updated fields, so that InnoDB can reconstruct the old version of the updated tuple. InnoDB uses undo log to first roll back a transaction. InnoDB also uses undo log to build the old version rows for MVCC. So with the help of undo logging, InnoDB places only the latest version of a tuple in the table file. The older versions can be reconstructed following the undo log chain of the target rows. So one secondary index entry is needed for each row. There is no need for multiple secondary index entries for each row version. Let's look at PostgreSQL. It has no undo log segment. If a row is updated, the full old tuple is just left untouched in the heap file, and the old versions form a chain. One secondary index entry is needed for each heap tuple in every secondary index, except the rare case of hot updates. This means index file bloats. To roll back a transaction, PostgreSQL simply leaves all the dead tuples as is in place. To do MVCC reads or writes, Postgres follows the version chain to find each row's visible tuple. This means a lot of random and excessive page accesses. To reclaim tuple space, InnoDB uses a vacuum technique, which causes massive buffer page evictions and massive I/O bandwidth consumption. Also, in each tuple header, there are 2 transaction ID slots. In PostgreSQL, a transaction ID takes 32 bits. So over a period of time, the transaction ID will wrap around. Postgres solves this issue also in the vacuum process by replacing the transaction ID with a fixed frozen transaction ID. So vacuuming is inevitable for PostgreSQL, even without updates or deletes. Next, let's look at the concurrency control of InnoDB and PostgreSQL. For InnoDB, it does MVCC for select statements, and it takes row or gap transactional logs for insert, delete, or update statements. By doing so, conflicting writes will all get a chance to execute and complete unless in a deadlock. So there will be no resource waste or jitters from the caused by transaction aborts. And conflicting row writes will always work on the latest row version. The issue for InnoDB is that there's a what you see isn't what you update or delete issue. That is, if you do a select first, then use the same filter criteria to update the same table's rows, you may not update the same set of rows as returned by the previous select statement, even if the two statements are in the same transaction. And the reason is that select uses MVCC, which does a snapshot isolation, but update use row logs, so it may update some rows that were not in the same snapshot as used by the select statements. This issue shows the significance for the update or delete returning statement, which is a feature that Kunlun storage has. Another issue of InnoDB is the concurrency impact when non-target rows are scanned and locked in repeatable read isolation level for updates and deletes. InnoDB may scan a lot of rows, but only update or delete part of them, but it has to hold all these transactional row logs until the transaction ends. In such a situation, InnoDB loses a lot of concurrency because other transactions may be blocked by this transaction. Next, let's see the concurrency control of Postgres. Postgres does MVCC for reads and writes, and this brings both strengths and weaknesses. First, conflicting writes under repeatable read isolation level causes conflicting transactions to be aborted. For example, if two concurrent transactions T1 and T2 both update to the same row R, and T1 updates R first, then T2 will block and wait for T1 to end. If T1 commits later, T2 will abort, and if T1 aborts, then T2 can proceed the update. This often causes a lot of waste of computing resources in heavily contended workloads because many conflicting transactions can be aborted. It also causes longer average latency and jittering latency and throughput. The good thing about Postgres concurrency control is that it takes no row or page level transactional logs for write workloads. That means trivial log system memory and time overhead, which is perfect for uncontended write workloads. In practice, it's often append-only workloads such as time series data. But Postgres storage format is row-oriented instead of column-oriented, so it's not perfect for time series workloads in terms of storage efficiency. Next, let's see the architecture aspect of Postgres and MySQL. Postgres has a multi-process architecture. It starts one backend process for each client connection. Such an architecture means a lot of issues for highly concurrent heavy workloads, which is typical of mobile applications. The big issue is that duplicated kernel data structures such as page tables have to be allocated for every backend process, causing massive kernel memory consumption. Here we made an example calculation, which is a typical database server setup in production. You can see in production setups like this, because of the excessive memory footprint of kernel structures, client connections can't be too many. Often, there can be no more than 500 client connections, which restrains the overall concurrency and throughput of IT systems. Connection pooling can solve this problem. Huge TLB technique of Linux can solve the problem, but it isn't always functional. In my case, I set huge pages to try in the Postgres configuration file, but I can see in proc meminfer that huge pages are not used. You can see the appendix page for my test machine information. And this multi-process architecture also means huge costs for context switches of backend processes, especially when memory footprint of kernel structure is huge, which impacts overall system performance. For MySQL, it uses a single process and multi-threads architecture for MySQL database instance, so that in the same example, no matter how many client connections are established, Only at most 500 plus megabytes of page table space is needed for the MySQL D process. Also, thread context switches are less expensive because they share the same page table and many other kernel data structures. Next, we will show performance comparison results between Kunlun storage and Postgres, and draw some conclusions from them, which consistently prove our previous understanding and analysis. Kunlun storage is Kunlun's storage node program. We developed it based on Percona MySQL 8.0.18. Postgres and Kunlun storage database instances are given the same amount of computing resources and are running with equivalent conditions and settings. For details of the performance tests, see the appendix page. This page shows the QPS of update index and update non-index cases. You can see that Kunlun storage QPS is higher than Postgres by 50% or more, and its latency is only half of Postgres and more smooth. And you can see from the curves that Kunlun storage is more smooth, and there are much less big fluctuations than Postgres. This page shows the QPS of OLTP write and read-write cases. Kunlun storage latency is 60% of Postgres and more smooth, and its QPS is higher than Postgres by 40% for write-only cases and 20% for read-write test case. So we can conclude that Postgres select implementation is more performant than Kunlun storage, although its insert update delete implementation is less performant than Kunlun storage. This is a complete conclusion of this performance test. We can conclude that Postgres read-only query processing is as good as MySQL or better. Second, we can conclude that client timeouts could happen occasionally or often under heavy workloads with Postgres. Third, we can conclude that IT systems using Kunlun DBMS will bring better end-user experience. Next, let's see Kunlun architecture, advantages and highlights. Basically, it's an introduction about everything about Kunlun DBMS. The components in the two boxes are Kunlun components. First, we have computing nodes, or CN. CN accepts client connections, requests, and SQL statements, and then interacts with storage shards to execute the SQL statements and reply results back to the clients. Storage shards store user tables. Each shard stores a subset of all user tables, and no two shards store intersecting user data. Metadata cluster is also a MySQL replication cluster. It stores metadata of one or more Kunlun database clusters. Finally, we have Cluster Manager. It interacts with MySQL instances of storage shards and metadata shard to keep MySQL replication node and cluster online status for all Kunlun clusters registered in the metadata cluster. Kunlun DBMS combines the best of MySQL and Postgres. It has all the core features of PostgreSQL. That is, the query processing, including most of the DDL and all the DML features. It has premium query processing performance, and in all the advanced query process features such as aggregates, window functions, stored procedures, and it has an open architecture. Kunlun DBMS also has the essence of MySQL, that is the InnoDB and binlog replication. It has premium performance in InnoDB for heavy workloads. This is amplified with our performance enhancements to MySQL XA transaction processing. It also has flexible high availability via binlog replication, and users can benefit from the open ecosystem using binlog. All the open source tools will be working with Kunlun cluster without any need to change. Also, MySQL DBAs and DevOps will find it very easy to work with the Kunlun DBMS cluster. They can use their MySQL skills as ease. The computing nodes of Kunlun don't need HA or any daily maintenance. All their states come from metadata shard, and they will simply work as if they were stateless nodes. Next, let's see the Kunlun advantages. First, its share-nothing architecture has great scalability, supports distributed transaction processing and distributed query processing, and it has elliptical scalability, has great crash safety, fault tolerance, and high availability, so that any node or network failure won't break transaction ACID guarantees. Also, all the Postgres connectivity work naturally with Kunlun DBMS. And we will also in future support MySQL client protocol and private DML grammar, so that the tools that worked with MySQL will naturally work with Kunlun DBMS without any change. Kunlun supports all common Postgres query processing features. Unsupported features are listed here. They are seldomly used anyway. Kunlun computing nodes are lightweight because they need no big shared buffer pool. They only access local metadata tables via the shared buffer pool. So in config file template, we set shared buffers to 4 MB, which should be sufficient for most users. So each backend process has no big page table, and this also makes context switching much less expensive, as mentioned earlier. Computing nodes initializes from metadata server, so DBAs don't need to do high availability for them, and computing nodes of a Kunlun cluster can automatically sync DDL operations so that clients can correctly connect to any of one of them to issue DDL and or DML statements, and all DDLs issued to any computing node will be replayed by all other computing nodes, and all computing nodes will execute such DDLs in exactly the same order, so that every computing node always has identical local metadata as other computing nodes of the same Kunlun cluster. Next, let's see some performance comparison between Kunlun storage and the Percona MySQL 8.0.22, which is the latest version of Percona server as of when this video is made. Let's first see what performance enhancements we did to Kunlun storage. We want to emphasize that performance issues we located and fixed exist in MySQL community version. They are not caused by Percona. Apart from this example here, we fixed a few other performance issues which are not open source in our community edition. And all performance numbers of Kunlun storage listed are produced by our enterprise edition, which can be downloaded in our website as detailed in the Appendix Page. First, some background info. In MySQL, a two-phase commit transaction contains two independent event groups in bin log. Each event group has a unique GTID. The official MySQL 8.0 clone mechanism requires storing GTID at each transaction's update undo segment header, at regular transaction commit, and the exit transaction prepare, rollback, and commit, so that a background thread called GTID persister will asynchronously and periodically flush GTID of each transaction's update undo log header to MySQL.GTID executed table. The problem is that when executing exit commit or the second phase, if a GTID slot has not yet been spared yet, the worker thread has to block and wait for GTID at the undo log header to be flushed, and then it's woken up by GTID persister after it has stored the first GTID to MySQL.GTID underscore executed. Then the worker thread can store the second GTID to the same GTID slot in its update undo log header. This is huge time and system resource costs from waits and context switching. What we did is to allocate two GTID slots in the update undo log segment header, one slot for each event group, so that worker threads don't need to wait for GTID persistor at XA commit, and XA transaction performance soared by over 200%. This change makes Kunlun storage data directory incompatible with data directories of official MySQL 8.0, and we verified that it works well with official Percona extra backup. We are happy to contribute this enhancement to MySQL and our Percona teams. Next, let's see some performance comparison numbers. We extended the sysbench by deriving some XA test cases based on existing update index and update non-index and OLTP test cases, so that every statement is executed in an explicit XA transaction. We name such cases with an _XA appended. QPS shown in the XA performance tests don't count non-read-write ops or XA start, XA end, XA prepare, XA commit commands. This page shows the QPS of update index XA and update non-index XA test cases. You can see the latency of Kunlun storage is 1/3 of that of MySQL, and the standard deviation of Kunlun storage is half of MySQL, which means much better end-user experience. That is, it's more smooth and quicker system responses. And we can see that QPS of Kunlun storage is 3 times that of MySQL for the 2 XA performance test cases. This page shows the QPS of OLTP XA write-only and read-write test cases. You can see the latency of Kunlun storage is half of MySQL, and the standard deviation of Kunlun storage is half of MySQL, which means much better end-user experience. The system will be more smooth and quicker when responding to client requests. And we can see that QPS of Kunlun storage is 2 times that of MySQL for the 2 test cases. So we can conclude that Kunlun storage shows 2 to 3 times better performance than community MySQL or Percona server 8.0.22. Finally, this is a performance summarization of Kunlun DBMS. Compared to Kunlun storage, there are a layer of computing nodes between clients and Kunlun storage shards. So there has to be some latency added for every SQL statement, caused by computing nodes query processing, that is, the parse, resolve, and optimization phases, and finally the local partial result summarization phase for selects. But Kunlun will outperform when a single Kunlun storage cluster has to scale out, because in that case, a single Kunlun storage shard will not be able to handle the massive heavy workloads. And also, more performance enhancements are on the way. We will release them in the near future. So we can expect that Kunlun DBMS will have better performance in the future. This is the appendix page. All the detailed information about the performance test and the Kunlun cluster can be found here. This is my talk. Thank you very much.